All good? All right. Thanks for your patience. Now we're online. Okay, can we get started? All right, thanks for your patience. So yesterday and then on Friday last week, we talked about physics-informed neural nets. And then today we're going to introduce this thing called the neural operators. So this is a slightly different way of learning physics using a neural network. Recall that the PIN was a regression model that regress against some sort of a physics state, and then in order to avoid the over problem and to inject some physics, it introduced some physics governing equation. So neural operator is a slightly different approach because in case of PIN, we had the issue where if the initial condition or the boundary condition changes, we couldn't do anything. So we had to retrain PIN whenever those conditions change, and that was kind of problematic from an engineering perspective, especially in a lot of engineering applications. We come across a situation where you have to run the same simulation over and over again with different parameters and things like that. And the hope is to use a neural network to accelerate the process, but in case of PIN, it wasn't possible. So whenever the condition changed, you had to retrain the model, and that was kind of annoying. So neural network could be a great alternative for those kind of situations. So in order to define neural operators, we gotta look into the theory of operators. The neural operator paper itself is a little mathy. There are a lot of function theory, functional analysis theory, and then the theory of operators and things like that. But today I'll try to introduce all this mathematical topics in a way that is easier and intuitive. So there are different ways of learning partial differential equations or some governing physics. So usually the solution to a partial differential equation is a time evolving sequence of those spatial snapshots. So this is a compressible flow case where you have a cylindrical cross section in the middle, and then the air is flowing around the cylinder, and then as the air flow around, because of this optical, we get to see the vortex shedding, behind the cylinder. We also see the formation of the bow shock and things like that. So at the end of the day, we have some sort of a video data, if you will, right? Now, the idea of physics-informed neural net was to learn the solution function itself directly. So the input to the neural network was the time and the spatial coordinates. And then at the end, we expected the neural network to spit out the physical value, right, at that given time and spatial location. So it's like, in case of a 2D simulation, you have a voxel, right, defined by the x, y, and then time axis. And then you're basically, going around this three-dimensional space-time using the neural network. So that's the PIN approach. But then obviously, we had issues, especially the issue of not being able to, incorporate different initial conditions and different boundary conditions. Now, instead of viewing the physics learning problem in this way, there is a different way of learning physics, which is the operator-based approach, and that's something that we're going to introduce today. So an operator is a mapping between functions. So a function is a mapping between some sort of a vector to some other vector, right? Or some scalar to a scalar. So those are the functions, right? We were, mapping a value to a value. Operators are essentially mapping of functions to functions. So you take a function as an input and then spit out a function as an output, as opposed to value mapping. So those are called the operators. So one way of viewing the problem of solving PDE is from the perspective of the solution operator. And what solution operator does is to take a snapshot at time t equal to 0, which happens to be a function defined over xy, domain, right? You take that function as an input, u of 0xy as an input to an operator, and that solution operator will spit out, yet another function at a different time t. And if we can find an operator like that, if we can find a mapping like that, then once we train the neural network on this operator, on the solution operator, and then whenever there's a different initial condition, we just throw in that different initial condition, and then based off of that initial condition, the solution operator should be able to generate the solution of your problem for that. Time varying sequence. So we can kind of reformulate the problem of learning physics into the problem of learning the solution operator instead of the solution function themselves. Does that kind of make sense? So a little bit of math. Like I said, function is a mapping from value to value. So these are the usual ones that we already know. So a sine function, for example, you take a scalar and then it spit out a scalar value ranging between -1 to +1, or a linear function is another function that. So a linear function usually takes a vector as an input and then spit out another vector as an output, right? So those are also value to value mapping. Now, operators, like I mentioned, is a mapping from a function to a function. And if you're in the undergraduate program, or if you're still, if you haven't taken real analysis or any relevant course, this idea of operator might be a little new, but you actually know quite a few operators already. For example, the differential operator is one of the very popular operator, right? And that you already know. So for example, given a function that is defined as 3x squared plus 2, right? A function as an differential operator does is to spit out a new function called 6x, right? Which is the derivative output. So that's a differential operator. The integral operator is another operator. So, the integral operator, for example, swallows a function, let's say sine x, right? And then the integral operator will spit out negative of cosine x plus a constant as an output, which is another, function. So that's another, operator that you already know. It's just that you never called it as an, integral operator or a differential operator. In convolutional neural network, the convolution operator is also an operator. So convolution operator takes an input, a function as an input, and then spit out some other function as an output. So that actually was a whole point of convolutional neural network. Some image come in, and we view an image as a function that is defined over a 2D domain, right? That function comes in, and then another function comes out as an output. So for more formal definition of how these operators can be used for solving partial differential equations, we're going to consider a generic family of partial differential equations. So we consider a PDE where on the left-hand side we have some differential operator LA, and A is, as we're going to see later, a set of physical parameters. So we already saw quite a few, differential equations describing some sort of a physics phenomena, right? And at the end of the day, you can write them all in a, generic form, without without losing generality. So we have this, differential operator LA acting on the function U, right? So that's what's happening on the left-hand side. And then on the right-hand side, we've been looking into the cases where fx equals to 0. So there's no external input coming to the system. But if you're a roboticist, or if you're working on some optimal control problems, fx is a control input. So the actuator output and those kind of things are defined on fx. So it's a very, very generic form of partial differential equation. Also here, we define the boundary condition. So at the boundary of a domain, we say that, in this case, we say that we have a Dirichlet condition where the value of U is 0 at the boundary. But later, we're going to actually relieve this constraint and then make it work for more generic family of PDEs. So, like I said, A in the subscript of the differential operator L is the space of physics parameters. So A, you can consider that as things like the density of material or permeability of some porous media, whatever physical parameter that might be. We define A as those physics parameters. And again, without losing the generality, we consider A as a function defined over a space, because some physical properties are constant everywhere, but there are properties that varies over space, right? So permeability, for example, varies over space. Porosity, density, those kind of things can vary across the space. And we use the term Banach space. This is kind of a technicality that is needed to define operators. So that's why that term is there. In a simple term, a Banach space is a complete normed vector space. So it's a vector space. It's a space of vector, but it is a normed vector space in the sense that we have ways to measure length and angles. Length and distance in that vector space, which is not always obvious. Okay, and then complete means that there's no missing points. There's no missing element in that vector space. So this is kind of a necessary condition to be able to for us to define an operator in this problem setup. So that's why we introduced this thing called a Banach space into the discussion. But if this whole thing is new to you, and if you have not heard the term Banach space before, or if you haven't done any real analysis or anything like that, don't worry. Just consider that as a space of a bunch of functions. Okay, a function, mathematically speaking, is viewed as a vector. So the notion of vector to a lot of engineers is just an array of numbers or some arrows floating around, right? So that's a perfectly valid view. But in pure math, actually we view vectors in a much broader scope. And things like functions are vectors in the sense that you can add functions, you can compute the dot product between the functions. You can also measure the norm of a function and so on and so forth. So you can assign the vector space property to arbitrary functions. And then the requirement for a Banach space is All right. So that was about the parameter A. Now we have U that plays an important role in this form of PDE. So U is our solution function. So that's evolving field, right? That evolves over time. And then again, we use the term Banach space, right? Over here. So again, the term Banach space is basically a set of functions, right? And a function in this context is a mathematical object that assigns some physical value to different locations in space. So U, for example, can be a function that assigns temperature at different locations in space, and that function will change over time, right? So that is kind of the dynamics problem that we're interested in solving. So D is the domain. D is the physical domain. So if you have a CAD model, then D is the space bounded by the CAD model. Or if you have some fluid system, D is the control volume. Yeah. Oh. Yes, yes. So for most of the physical systems, it's either 2D or 3D, depending on how you model it. Sometimes in toy problems, we use one-dimensional space, right? 4D and 5D, conceptually, yes, you can, yeah. Um, Now, the F, like I said, is a source term. So unlike the pin formulation that we saw so far, F is a source term, that comes from the control inputs, or things like that is modeled as F of X. And D over here, like I said, is a bounded physics domain with the lowercase letter d as a dimension. Now, the main thing that we're learning today is this operator LA, okay? So as you can see over here, this LA maps from the parameter Banach space. So what that means is it's a set of functions that defines the physical parameter at different. So we go from the space of those parameters to the space of linear operators. And the linear operators themselves, what they do is to go from a function u to another function f. So we're defining the relationship between functions to functions, and that is the space of linear operators, L. And then that linear operator is generated from physical parameters, okay? So that is, kind of, the setting for the operator learning problem. So the solution operator to this PDE is obviously a mapping G, okay? A mapping G that sends, from the A cross U star. So A, again, is the parameter Banach space. So that's the space of physical parameters. And then U star, which is the space of Fx. So you have some physical parameters and then control inputs, that comes to the system. From there, you want to predict what's going to happen in the future at some arbitrary time t, which is the space of another Banach space of function u, right, that we're interested in predicting. So there are lots of mathematical terms, and I'm introducing this because, a lot of neural operator papers will talk about, things using these jargons, okay? Things like Banach space, things like, operators. So you got to know the basic keywords in order to be able to read those papers and understand what's going on. So that's why I'm introducing, a lot of those, but none of us are, pure mathematicians, right? So we don't really care about the proof and, things like that. And then at the really high level, as long as you understand, the term Banach space is just a set of functions. Then the term operator is a mapping between functions to functions. That's probably all you need. And when you read the paper or when you come across anything related, any scientific articles related to neural operators, don't get intimidated by those terminologies, because if you don't have the applied math or a pure math background, terminologies might be a little intimidating. But at the end of the day, it's just a fancy way of saying that, oh, we're going to learn a mapping from a function to function, or a set of functions to a set of functions. Yes. Well, to be precise, we have three different Banach spaces: A, U star, and U. Yeah. So yeah, but they look all the same, so you can treat them as the same thing. No. So they have different physical meanings. So it's not like, one is a subset of the other or things like that. Those are three different spaces that correspond to, three different physical quantities. So A is a space of parameters. So things like, Reynolds number. Well, the Reynolds number is not a good example because, that's usually constant everywhere. Yes. Things like density, right. So A will obviously affect you, but that doesn't mean that A is the same as you. Yeah. Right. Right. Yeah. So these quantities, the parameters, and the control function affects the final response of the system, is how you should understand this. Other questions? Yeah, this term over here. So again, this is the technicality from the applied math perspective. So because we have an operator connecting two different function spaces, we call them duals. Yeah. But I guess, again, if this confuses you, just treat U star as a separate space than, U without a star. Okay. So we have some space of functions and we have another space of functions, and then we want to find the relationship. Every vector space has its dual, yes. There are duals in the sense that we have a linear operator, and then with respect to this linear operator, these are duals. That's it. I wouldn't put too much of a physical meaning. It's just the mathematical technicality. So, yeah. Okay. All right. Congratulations. You survived this slide. Okay. You survived this slide. At the end of the day, what we're interested in doing in neural operators is to parameterize this solution operator G using some sort of a neural network with a set of parameters theta. And there's a thing called the universal approximation theorem for operators. So it's kind of the same theorem as the one that you already saw in Professor Khanna's lecture. But universal approximation theorem says that if you have a sufficiently large number of neurons, then you should be able to approximate any arbitrary operator using that neural network. Okay, and then there's a formal proof there. But again, none of us are mathematicians, so we're not interested in the proof. We just embrace that as a fact, right? So the good news for you is that no matter how complicated the solution operator is, in principle, you should be able to model that using some sort of a neural network, given that the neural network is deep enough or wide enough. Okay. Now, after all this mathematical definitions and things like that, at the end of the day, neural operator is just a fancy way of calling image to image mapping. Okay. Function to function mapping. In computers, there's no continuous function. So a function defined over a physical domain is essentially an image, right? So you have an image, and then you have another image, and you want to learn the mapping between the two. Is essentially what it's saying. And the actual mathematics, actual implementation of neural operators, if you look into it, it's simply a neural network mapping an image onto some other image. Even the authors of this neural operator paper, at the end of the day, they say, oh, operator learning is simply an image to image mapping problem. Yeah. So yeah, that's exactly the face of my own graduate students when they first saw this neural operator stuff. They were initially intimidated by all the math and blah blah blah, and then at the end of the day, the conclusion was, "Oh, this is a neural network that takes images and input, spit out images and output." That's really what it is. Of course, we talk about all this mathematical technicality because we're going to actually generalize this to something more interesting configuration. So even though in a nutshell neural operators are image to image mapping problem, it's useful to understand the terms like Banach space, solution operators, and blah blah blah, because as we'll see later, those are the ingredients for the physics learning problem. Okay, and without those ingredients, then PIN is probably the best thing that you can have, which obviously has a lot of problems. So given that a neural operator is essentially just the image to image mapping neural. The image could be various different things. So for example, an image could be a snapshot of the solution function at a given time t. So that's usually the output that we want to predict, right? So snapshot of a velocity field at an arbitrary time t, you want to predict that, right? From things like, for example, initial condition or initial configuration of the physical system. So this is what the system looked like at time t equals to 0, given as a function, given as an image, right? And from that image, let's say you want to predict a snapshot of the physical system at an arbitrary time t, is usual, prediction problem. Another thing that could be considered as an image is the boundary geometry. So let's say you have some, interesting looking pipe, and then you want to, analyze the fluid flow inside of that pipe. Then that geometry of the pipe could be represented as some sort of a binary image, where inside of the pipe is filled with ones, outside of the pipe is filled with zeros, right? So from that boundary geometry as an input, and then maybe some other images as additional inputs, what is going to be the flow at time t equals to some tau, could also be a problem that you might be able to solve. System coefficients, so things like the density, things like porosity of porous media, a lot of different things can be again represented as a function, right? If you have a constant value such as Reynolds number, then you can just consider a constant function where the function is with all the same number, or the image is filled with the same number everywhere. So depending on the physics problem, there can be many different images, and then what neural operators do is essentially find the image to image mapping. Okay. Yes. Coefficients of the differential terms? No, no, doesn't have to be. Well, linear operator. So the term linear you have to be careful. The term linear means that the output of the operator is the final, object that we're interested in finding, instead of, as opposed to, the output of the operator goes into some other operator, and then, mixed up together. In that case, we don't call it a linear operator. But it doesn't mean that, this operator is comprised of linear coefficients. Does that make sense? For example, yes. So yes. So mathematically speaking, linearity is defined as, by two things. One is, you can add u and v first and then apply operator, and that will be the same as u and v separately and then add them up later, right? So that condition is the first thing. And then the other thing is when you multiply a scalar, you multiply scalar and then put in the operator, versus you put in the operator first and then multiply the scalar on the output, the result should be the same. So as long as, your object, your operator, satisfy those two conditions, you call it a linear operator. And again, that doesn't mean that, the actual expression of the operator is comprised of all the linear terms. Yeah. Okay, so to help you connect the dots a little better, here's an image-to-image problem. Here's a physics problem that can be considered as an image-to-image problem. So the Darcy flow is a flow of water, basically, or flow of some fluid inside of a porous medium. So when you have I don't know, like on the ground, you have a compound of stones, sand, and various different materials. You pour water, then depending on the composition of the rocks and sand, right, the water will flow eventually, but the rate of flow is going to change, right? So Darcy flow is basically, or the Darcy equation is basically the equation describing how that fluid flows inside of those porous media, and it basically looks like this. So compared to the other, toy problems that we've seen so far, it looks slightly more complicated. But at the end of the day, we have the gradient operator and the divergence operator acting on the function u, okay, an image u. And then what that operator does is to relate the solution u with the source term f. Okay. So here in this example, we just assume that the source term is 0. So there's no additional fluid coming in to the system, but we consider that there's no source generating or making the medium disappear. So f equals to 0 is the assumption. A is, physically speaking, A is what's called a permeability coefficient. So how well the water can flow at that given location is defined by this coefficient A. And then what's interesting about this equation is that the A is actually a function. Okay, A is an image. So for example, we have a permeability coefficient, defined like this. We have kind of two-phase flow, right? So the yellow is where the water can flow faster, and then the purple or the navy is where the water flows slower, right? And we have kind of a two-phase, binary phase permeability defined like that. And given those conditions, so f equals to 0 everywhere, plus the distribution of A, what is going to be the pressure inside of the porous medium is kind of the question that we want to answer in this toy problem. And the solution operator G, okay, will take the constant image F and a constant, a variable image A as an input. And from those given inputs, we would like to make a prediction of the pressure distribution is what's really happening over here. So in terms of, training the neural network, here, since F equals to 0, that constant image and on the permeability coefficient. So at the end of the day, this is it. This is what we're doing with the neural operators. For a given image, we want the neural network to be able to generate a new image. Okay. And let's say we have hundreds of such pairs in the training data set. So what you ought to do is to, train the network to be able to, perform that conversion or the translation from one image to another image. And then, you train that model with some sort of a loss function. So it can be an MSE loss, mean square error of the predicted values, or it could also be some other, loss function that you can define. So at the end of the day, neural operators is nothing more than just an image to image neural network. Hope you're disappointed. Sure, sure, sure. Yeah, that's a good point. So in case of a harmonic oscillator, the left-hand side, the image could be the angular frequency and the damping coefficient. And then the output could be the trajectory or position at arbitrary time t, right? And then you can train the neural network in that. Same thing. You just have multiple images as an output. That we'll see tomorrow. Yeah. So that kind of a rollout of prediction is what we're going to see tomorrow. But neural operators are essentially just, if you want to predict a sequence of, images, then you just add more, outputs to the neural network. So instead of predicting just one image, you can make the neural network predict 10 images in sequence. Yeah, exactly. Hmm. Hmm. Yeah, you can use it that way, but usually the neural operators are not defined to. So you could use the neural operator in a way that you put in the snapshot at t equals to 0, get an output for t equals to 1, and then that goes as an input to the operator again, and then generate a output for t equals to 2, and then that goes back again as an input, and then keep predicting the future. So that is something that you can try, but the problem is the neural operator predictions are not guaranteed to be continuous. So you may end up predicting a sequence that is not continuously varying. So that's the part. So neural operators, you have to be careful when you use it that way because there's no continuity guarantee. Whereas the method that we're going to see tomorrow actually does that. So an input of a snapshot produces a snapshot after time delta t, and that output can is fed again as an input, and then we predict another output after yet another time delta t, and so on and so forth, so that we can kind of roll out an entire prediction. And for that one, there's a guarantee that the things are continuous. So yes. Hmm? Yeah, yeah, yeah. You can view it as RGB layers, or I mean, the whole idea of convolutional neural networks can be generalized to any arbitrary dimension. Yeah. So it's basically the same thing. So if you have a 3D, volume image, then you're going to need to apply 3D convolutions. But the way that 3D convolution works is basically the same as a 2D convolution. It's just one more axis in the tensor. So, all right. So at this point, you might be a little disappointed because we started with this horrible looking mathematical theory of finite space, operator theory, and so on and so forth. We talked about a lot of stuff, but then turns out it is basically an image to image problem. And you may wonder, how is this different from the usual computer vision models, where you take an input, right, an image as an input, and it spit out an image as an output. So what's the difference between neural operator versus those usual computer vision models? Well, in terms of the scientific contribution, there are actually quite a few. So even though I introduced this as an image-to-image neural network, the actual implementation contains a lot more desirable features, okay, than the usual computer vision models. So that's something that we're going to be, talking about first of all. The second thing is the idea of neural operator is not actually exclusive of or conflicting with the idea of physics informed neural networks. So at the end of the day, when we train the neural operator, right, you have a predicted output, and then you could actually add a physics informed loss, if you know the governing equation, into the loss function, and then you can convert this neural operator into a physics informed neural operator, or PINO. So these are not the two kind of competing notions, but I guess neural operator is more about the way we design the neural network and how we view the problem. So with that being said, here's a little closer look into the neural operator paper. The difference between neural operators and the usual computer vision models is that the usual computer vision models, works on basically pixels, right? You have some predefined pixel grids, and then you want to learn the mapping between pixels to pixels. For neural operators, we're going to introduce a trick to make it continuous, so that even if the grid size varies across your data set, you can still use the neural operator with those varying grid size taken into account, so that when you have a scarce grid, you can make a prediction that corresponds to that scarce grid. When you have a denser grid, then the same neural network can be used to make prediction on a denser grid. And as a matter of fact, neural operators being a continuous mapping between functions to functions, any arbitrary discretization it should be able to handle, versus the usual pixel-based image to image mapping algorithms. There's no such a notion of discretization or anything. You just handle pixels pixel values directly and then convert pixel values into different pixel values. So here's how they, achieve that kind of, continuous mapping. So, if we simplify the problem into one-dimensional functions, so we have a one-dimensional domain X, and then we have a function defined, and then here we're talking about, sort of similar to the permeability, the Darcy flow problem, where we have the, parameter defined as the blue curve, and then from that blue curve, we want to be able to predict, say, pressure distribution, for example, which is the green curve, right? So in 1D, now it's a curve to curve mapping, right? And then the operator that we're interested in learning, the operator G, is basically the convergent rule from one curve to a different curve. Okay. Now, in computers, obviously, there's no way to have some continuous values. So your data will be given, according to some sort of a discretization, right? So if you have a sensor measuring a signal, then that sensor may have certain frequency, right? And that's what defines the discretization of your continuous signal. If you're doing FEM or CFD, then you gotta construct a grid first, and then that grid is basically how you discretize the space, and so on and so forth. So without loss of generality, we assume that there is some discretization. So X, the continuous interval X, is now divided into some discrete sequence of values xi. And for those xi's, we have the measurement ai, okay, for the function a. And then similarly for the domain y, for the green curve, we assume the same scenario. There's some discretization of y. And then for each given yi, we have the value u given as the data set. So in that setup, now we have a vector, an array of AIs, right? And then we have an array of UIs. And the neural network, okay, if you don't, if you do it in a naive manner, a neural network will basically take in, n plus on the output node, right? And then basically, for different outputs, we have a different combinations of weight values, right? So in an equation, this is basically how we define the relationship between inputs and output inside of a neural network, right? Now, if the discretization changes, okay, so for some reason, you've been measuring something using a 100 hertz, sensor. So 1 second you have 100 measurements, but then, you upgraded your sensor. Now, new sensor can measure 500 hertz. So we have five times more, much denser signal coming in. But then, with the traditional neural network, you'll have to throw the previous result away, or, maybe downsample your new to 100 hertz, right, back into 100 hertz. But that's not, really desirable. The good news for you is that the neural operator approach actually allows you to handle those kind of different discretization. So even if the network is trained on one set of discretization, you can still use it for other set of discretization. Or even better, if you're training data, you can have multiple different discretization. So in your training data, you can have their signals coming from 100 hertz, and the sensor signals coming from 500 hertz, and mix them together, still train the model. Okay, that actually is the part that I consider as the biggest, scientific contribution of this neural operator paper, not the idea of image to image mapping, which may sounded boring, right? I mean, what's new about image to image mapping? But this is really the important the concept that neural operator paper introduces. So here's a trick. What the neural operator does is to consider some sort of a continuous indexing of the weight value k. Okay, so in the original formulation, we have the discrete indices ij. Okay, so kji is the weight value connecting the ith input a with the jth output u, right? Uj. So we have some n by n matrix, right, filled with those discrete values that connect, the ith, value in the input signal with the jth value in the output signal. So that's what happened over here. Now, instead of that discrete formulation, we slightly changed the definition of the neural network into the form that contains a continuous kernel. Okay, and this kernel is kind of like a function. Okay, that takes the value of xi and the value of yj, and then spit out some, adequate weight value k as an output, so that even if the discretization changes, since k is some sort of a continuous function, a kernel, okay, that correlates the input x and the output y, in theory, you can have any kind of arbitrary discretization and still make this thing work. All right. So yeah, so as a matter of fact, this formulation, okay, this little trick of converting this discrete into, converting this weight with the discrete index to a continuous weight with the continuous index is actually the generalization of the Riemann sum. Okay, so I don't know when you learned this in the Indian curriculum, but either in high school or in first year in college. Yes, yes. So either in high school or in the first year in college, you learn this relationship that the integral of something is essentially just the infinite sum of, right? So this formulation over here, if we consider this capital letter K into the the kappa kernel kappa times delta x, then this is essentially the same as the Riemann sum of this integral. Of course, in the paper, they mathematicians, they love to intimidate people, so they introduce this first, and then keep talking about, oh, this is a continuous kernel, this is equivalent to a neural network, blah blah blah. So if you read the paper for the first time and see this, you may wonder, what the hell this guy is talking about. But as a matter of fact, this is the important part. This is the key idea over here, where the neural network weights are actually represented as a function, not a fixed, discrete value anymore. Now we have a function k, or the kernel function k, that correlates any arbitrary input x with any arbitrary output y and any arbitrary positions. Okay. So with that, okay, formulation, What is possible now is you can have any arbitrary discretization for X, and you can have any arbitrary discretization of Y. They don't need to be compatible at all. It can be any, arbitrary discretization, on each of the domain respectively, and still the kernel function kappa will be able to connect those, different locations somehow, right? And then this is how we define a neural network layer for the function to function learning problem. Okay. So we have a slightly fancier expression of the usual perceptron, which involves the integral and the kernel operator. But at the end of the day, this is basically perceptron, right? So here's a demonstration of how this kernel function and the integral works. So you take, an arbitrary input at location X. So that value of X goes into the function A, as well as the kernel function kappa. And then let's say you want to evaluate the value of U at some arbitrary position Y. Then that also goes into the function kappa. And as a whole, now you can calculate the integral of this, followed by some activation function. So this can be ReLU or, the SILU or 10H, whatever it is. Then, that's basically how the prediction of UY is performed. Of course, not just this particular Y value or the particular X value. You can evaluate any combination of X, Y, right? In this formulation. So that's kind of the nice thing about this, right? Now, if you think carefully about this, you may notice one problem. In case of the perceptron, in case of usual neural network, the value of Kij, okay, we associated the values of Kij at different neurons, right? And the neurons are discrete. Neurons are not continuous. So we could have, for each of the connection in the neural network diagram, whenever there's a line connecting two nodes, right? We could assign a weight, right? But now that we have a kernel function, okay, how do we implement a neural network layer, right? Could be a question. So it sounded like, okay, step one, learn kappa, find kappa, and then using that kappa, compute the integral. And then that sounded like basically the implementation of the neural operator. But if you think carefully about it, the actual implementation is not so easy, right? So there are two things, two questions. How do we calculate the kappa, the kernel function, is one thing. We got to find a way to somehow model this. And then also the integral. Whenever you see an integral operator, you have to be concerned, because integral is something that it requires a lot of computational resource to compute. It's not easy to compute integral. So how do we do those two things is kind of a practical consideration for the implementation of the neural operator. So to this end, the authors of the neural operator, they propose 3 different methods, okay, to facilitate the calculation of the kernel function as well as the calculation of the integral, okay? One of them is called the graph neural operator. And the idea of graph neural operator is to model this or approximate this continuous kernel function K, kappa, using a discrete graph structured data. Similar to finite element analysis, you're basically setting graph nodes, and then let those graph nodes determine the continuous function kappa, is kind of the idea behind the graph neural operator. And then the integral, right, in the graph setup is basically just the addition of the individual node values. Again, similar to finite element analysis, right? You divide a large complex physical system into smaller elements. And then once you determine the values at each element, at the end, you just add them up to compute the integral, is what you do. So graph neural operator is basically that idea applied to neural operators. Low rank neural operator is a slightly different approach where because the kernel function and the integral is difficult to evaluate, we're performing what's called a low rank approximation of those complex functions is the idea behind the low rank neural operator. And then finally, we have a Fourier neural operator. And then the Fourier neural operator, the property of Fourier transform actually allows you to convert the integral into basically the summation. Actually, as a matter of fact, the integral of the kernel function, convolved, against a given function, if you send it to the Fourier space, it becomes nothing more than a dot product between Fourier coefficients. So they propose these three different methods to implement the neural operator and then make it work in a continuous setup. In today's class, we're going to focus on the Fourier neural operator. Graph neural operator is pretty easy to understand. So, even if I don't explain this to you, you should be able to read the paper and then still understand what's going on. Low rank neural operator is also pretty simple, although I guess nobody uses low rank neural operator these days. So it's either graph neural operator or the Fourier neural operator. And then, there are some variants of those two. So as long as you understand the Fourier neural operator, I think you should be able to, actually read the paper and then understand what's going on. So a little more into the Fourier neural operators. So this thing called the convolution theorem, if you're from a signal processing background or, yes. Yes, it's a combination of sine functions and cosine functions. We don't actually assume a particular function form. We just, in case of graph neural operator, we use the graph to represent, whatever arbitrary function that, that might exist. So for the kernel function, we do not assume a particular function form. And then for the Fourier operator, I mean, given that you have infinitely many sine waves, right? You can represent any arbitrary, function is the Fourier theory. Yeah. For graph. No. Even if each of the element has a shape, a shape function, for the entire domain, it can be any arbitrary function shape, right? So even if no, we don't assume anything about the function shape. Yeah. So evolving in what sense? Like the dynamics, time evolution, are you talking about?
So I don't know if I understood your problem correctly, question correctly, but the kernel function, once it is learned, stays the same. And yeah, the once we train the kernel function stays the same, and it's not evolving. It evolves during the training, obviously, right? You update the model parameters, and then the kernel function may change during the training. But once the training is done, the kernel function stays the same. Does that answer your question? Yes, sure, of course. If you add more data, update the model, then yeah, the kernel can change. Yeah, I mean it's kind of a continuous learning process, right? Is there a question? Yeah, so we're learning the kernel. So similar to the previous case, the usual perceptron case, we're learning the kernel. Except the kernel is, yeah, we're learning the kernel. It's the same thing. This is the input to the neural network. The activation function is fixed. This is the output. So the only thing that needs to be determined is the kernel. In case of the perceptron, the kernels were defined as a discrete collection of values. It was a matrix, right, that we learned. Now we have a continuous function, okay? So the learning problem is a little more complicated because we have a continuous function. And then to model that continuous function, we can either use a graph, right? And in that case, graph may have, well, in that sense, we're assuming something, about the function, right? The graph may have the shape function to borrow the finite, element, lingo. Or in case of Fourier operator, we're gonna see soon that we're basically learning some Fourier coefficients. Yes, in the Fourier basis, so that we can learn this kernel by updating those Fourier coefficients. Yeah. Does that make sense? Okay. All right. So to understand the Fourier neural operators, the key thing here is what's called the convolution theorem. So the convolution theorem suggests that if you have a functions f and g in the original function space, then that convolution in the Fourier space, so after the Fourier transform, the Fourier transform of the convolution of the two functions is the same as the dot product or Hadamard product between the Fourier coefficients of f and the Fourier coefficients of g. So, if you have a convolution of two functions and I want to take the Fourier transform of that, you can do the same thing by simply taking the Fourier transform of the individual functions, okay? So Fourier transform of f and the Fourier transform of g. And then as a result of the Fourier transform, you will basically have a set of coefficients. And then this Hadamard product is basically an element-wise product, okay? And then you take the element-wise product of those coefficients, and then you get a new set of coefficients as a element-wise product, and that is essentially the same as the Fourier coefficients of this entire f convolve g, right? is basically what's called the convolution theorem. So if you're from a signal processing background, you've probably seen this many times because that's, kind of bread and butter for the signal processing people, right? So you have like, any one-dimensional, two-dimensional, any arbitrary dimensional signal per se. If you want to compute the convolution of those signals, this is kind of the nice property that you can use. Why does that matter to us? Because this integral operator that defines the continuous perceptron is essentially the special case of a convolution operator. Okay. So the convolution operator, so the convolution between kappa and A is defined as the integral of kappa of y minus x. So the kappa is now a function that takes a scalar value as an input or a single value as an input. And then you compute the integral between the two. So that's the definition of convolution, right? And then this is a generic form of that convolution operator, which means, in a different perspective, the original formulation, the rigorous formulation of the integral operator, we introduced the assumption that kappa of yx equals to kappa of y minus x, right? With that assumption we introduce, then this whole integral operator thing can be understood as a convolution between kappa and A, which means after the Fourier transform, okay, this whole integral operator to define the continuous perceptron is nothing more than just the element-wise product between the, the Fourier coefficient of A and the Fourier coefficient of kappa. Okay? And then the actual kappa itself, we don't even need to, learn the actual kappa. We just need the Fourier coefficient R. So R is basically the parameter that you're trying to learn. And then, during the training, the values of R will get updated. And then whenever the input comes in, we perform the Fourier transform of that input signal, compute the element-wise product with the model the parameters that we learned. And then after the element-wise product, we take the inverse Fourier transform. And that is essentially the output of this integral. Does that make sense? So this whole integral and the continuous kernel has become simply an element-wise product followed by the inverse Fourier transform. Okay, so you don't actually need to compute the integral. You don't actually need to, worry about representing this continuous function kappa. Everything just happens in the Fourier space. You just need to multiply element-wise. So it, at the end of the day, becomes the usual, neural network operation. You have a vector, take the sort of a dot product, not exactly dot product, element-wise product of those coefficient vectors. And that's essentially how you could implement the operator using Fourier transform. So inside of the neural, implementation of neural operators, you will see basically these three steps. One is the Fourier transform of any given input signal A. So whenever input comes in, a Fourier neural operator layer will first perform the Fourier decomposition of that input signal. So any arbitrary function will be decomposed into a bunch of sine waves. And then the coefficients associated with different sine waves. And then over there, we perform a linear transform R. So that's the learnable parameters inside of the neural network. So we start from the random, coefficients R. But then as we repeat the training, the values of R becomes, more specific. And then as a result of that, linear transform, we'll have a set of new Fourier coefficients. And then by taking the inverse transform of those coefficients, you'll basically be able to, reconstruct a full sort of a continuous signal, right? And then this is how you define a perceptron with continuous input and continuous outputs. Okay. So this is kind of a really nice trick that can be applicable to any arbitrary function with any arbitrary discretization. There's a little bit of overhead, obviously, because you have to perform Fourier transform. But fast Fourier transform is an algorithm that can facilitate the calculation of Fourier transform. The computational overhead is not going to be terrible, right? So in that way, you can achieve a continuous function to continuous function mapping. So here's kind of an interesting comparison between the usual neural networks versus the Fourier layers. So the usual neural networks, the weight values, the convolution filters, right? At some fixed pixel values, right? And then the filters in CNN basically learns those kind of tiny little patterns, and then you combine them to construct more complete sophisticated pattern. Fourier filters, on the other hand, we have continuous. So no matter how much you zoom in, you still be able to have a really fine resolution, because in theory this is continuous, right? You basically have sine functions with different frequencies, and then as a combination of those sine waves, you can generate lots of different patterns. So the Fourier layer is basically like the convolution layers, except that the filters are represented now as a continuous continuous function. The other thing is the Fourier transform is applied to the entire domain. So in case of CNN, we define the convolution kernels at like 3x3 kernel or 5x5 kernel, and then we kind of scan that convolution kernel over an image, versus the Fourier kernel defined over the entire image domain. So Fourier filters are better at capturing global kind of trends inside of the image. Almost there. So the full architecture of Fourier neural operator looks basically like this. So again, some input signal come in, input image come in, and then that input image gets pre-processed. And then basically you apply a bunch of Fourier layers. And then at the end of the day, we have a post-processing layer Q. And then finally, we produce the final prediction output U. Okay, so a continuous function with an arbitrary discretization come in, and then a continuous function with an arbitrary discretization will come out. And each of the Fourier layer, like we just saw, we have the Fourier transform, linear transformation, and then the inverse Fourier transform. There's an auxiliary pathway. So this is kind of a parallel connection inside of the neural network. And then in this, what's called a skip connection, we apply the local pointwise linear operator. The point of doing this is because when we do the Fourier transform, especially for the computational concerns, we do not use infinitely many sine waves. So remember, when you do the Fourier transform and you can afford infinitely many sine waves as a basis, functions, then you should be able to, construct a precise, reconstruction of the original function. But then if you limit the number of, Fourier bases, then, you can only have low frequency signals and then you will lose a lot of high frequency signals as a result of that, right? So this is sort of low pass filter in some sense, because we're going to be using a smaller number of sine waves, right, with a relatively longer or small frequency, and because of that, we're losing a lot of details, right? If we just naively use this pathway. So what happens is for whatever input signal come into we take a copy basically of that, and on the top we add this low frequency signal, is what's happening over here, and W is simply just a scaling factor to kind of balance the scaling between the Fourier output versus the original input. And that's essentially how you would implement a Fourier layer inside of neural operator. So after the break, we're actually going to see the implementation of the Fourier convolution. Okay. The good news is that the PyTorch already comes with the fast Fourier transform implemented. So you will see that this whole implementation is essentially just the same as the perceptron, except that before, right after the input come in, you perform the Fourier transform, and then right before you spit out the output, you take the inverse Fourier transform, and that's pretty much it. So far, so good? Yes. No, go ahead. To be rigorous, yes, you're right. Although in a lot of implementations, they just choose an arbitrary number of bases. Yeah. Hmm. So for those cases, you can just set this as a continuous function. So regardless of the input x, it'll just produce the same output, right? And then still use the FNO. Although I would argue that that's not the most efficient way of constructing the model. So in that case, you will need to make some treatments to make the computation more efficient. So the specific case of the problems that neural operators are designed for are the problems where the input condition has some variance of over space, right? If you have like constant properties like Young's modulus, for example, or some aggregate material properties, then neural operator may not be the best choice. Yeah, good question. All right. Graph neural networks. We're not going to actually implement this, or we're going to go too deep into this. But just to give you an idea, graph neural networks. Graph neural operators. We basically introduce a graph to approximate a continuous function. So in case of Fourier neural operator, we introduce a Fourier basis, the decomposition of an arbitrary function into sine waves, as a way of representing a continuous function. Graph neural operators, we're basically introducing a graph to represent a any arbitrary continuous function. In case of FE or other numerical literature, we introduce things like shape functions, and we make some assumptions in terms of how individual elements look like. So the simplest thing to assume is that again we assume that for each of the element there's a linear gradient, right? Is what we usually assume for the simplest case. And then from those assumptions, we kind of stitch the elements together to construct a bigger picture. Inside of the neural network, however, even that shape functions are assumed to be learnable. And then the way that we learn that is, I mean, there are many different ways. So what the authors introduce is, this thing called a message passing neural network. And this message passing neural network basically defines, quote unquote, the shape function at each of the element. And then, from that learnable shape function, we're basically representing, any arbitrary, kernel that we're interested in calculating. So the idea of message passing, this is not the main thing, main focus for this course series. So I'm not going to go too deep into this whole thing. But the idea of message passing is that, given a graph structure, okay, where each of the vertex has some feature vector describing that, that node, and then each of the edge also have a feature vector describing that connection, okay? And then the idea of message passing is to aggregate those edge features and the vertex features, okay? Using some sort of a linear sum, okay, inside of a local neighborhood. So Ni is the one ring neighborhood of the vertex I. And over that one ring neighborhood, we're basically taking the average, some weighted average of the feature vectors, okay? And then from there, we're updating the feature values at each, vertex location, okay? And then by repeating this multiple times, so that is what, that one cycle of taking the local summation is what's called a one round of message passing. And then basically by repeating the message passing multiple times, then you can define the shape function over some n ring neighborhood, okay? Again, for the details, I'm not going to go too much into the message passing algorithm. Message passing is just one recipe. There are many other, methods to define, graph operations. So there is this whole, literature about graph convolutional neural networks, graph artificial neural networks, all this kind of stuff. And, even for message passing, there are many different recipes. So I guess for the particulars of the message passing and then the graph layers, I'm not going to go into the details because that's beyond the scope of this this course. But at the end of the day, assuming that you have some recipe, right, to combine the local nodes to produce a value, essentially what we're interested in doing using message passing network is to model this kappa, the kernel function kappa, through message passing, okay? So that, again, for any arbitrary graph discretization of your three-dimensional or physical domain, any arbitrary dimension, for any arbitrary graph representation, now, because of this message passing, you can, produce the output on the graph nodes. And, that's really, what it is. So in terms of the PyTorch implementation, this one is even simpler. In case of a layer, you had to define the fast Fourier transform, and then you had to, define all these operations internally. The graph neural operators, you basically just borrow a message passing layer in PyTorch, and that's pretty much it. Okay. All right, so finally, by implementing all this, these are some examples of what neural operators can do. So sort of going back to the earlier question, from an initial vorticity. Now we have a fluid dynamics problem. And then this is basically the solution of Navier-Stokes. And you start from this initial distribution of vorticity. The velocity field evolves over time. And then the neural operator is designed to, predict a sequence of snapshots. So there are 4 image outputs from the neural operator. That corresponds to t equals to 15, t equals to 20, t equals to 25, and t equals to 30. And then if you, the bottom row is the prediction. And if you compare that with the actual numerical simulation result, you can see that the patterns are, pretty much the same. Of course, you can change the initial vorticity and then put it in the same model without retraining. And then you can get, different vorticity patterns. And then according to their demonstration, neural operators are able to, predict those, the fluid pattern given different initial vorticity. Here's another interesting use case. Actually, NVIDIA is quite vested in the neural operator for some reason. So NVIDIA Modulus is a library, a collection of implementations of all kind of physics-aware deep learning algorithms. And then a quite significant portion of NVIDIA Modulus engine is neural operator implementation. So here's the use of Fourier neural operator for the prediction of the weather, change. And then I think, to talk about the technicality a little bit, because the Earth surface is not the usual Euclidean space, but it's a sphere. So they actually defined a spherical Fourier transformation. And then using that spherical Fourier transformation, they defined the Fourier neural operator layer, spherical Fourier neural operator layer. And then from there, they were able to predict, I think this one is the temperature field. And then you can see that because of the wind and the water current, you can see that the temperature field kind of changes. And then obviously, once you train the Fourier neural operator in this way, then for any given initial condition, any given snapshot of the temperature field under our surface, you'll be able to predict the future state is kind of the promise here. Here's a little more. I think this one, we're back to Navier-Stokes again. So we have the vorticity, and then the velocity field, the x component of the velocity and the y component of the velocity. So on the top row, we have the true, signal from the direct numerical solver. And then the bottom row is the prediction result from the neural operator. And you can see that it's actually pretty good, right? If you look at the prediction result. All right, so main takeaways. The idea of neural operator, we're interested in predicting image-to-image mapping as opposed to solving PDE. So PIN, physics-informed neural network, was more focused on solving the PDE, right, using neural network. And because of that, each time you have a different physical parameter, each time you have a different initial condition and boundary condition, you have to solve it again, as like what you would do with the traditional numerical solvers. Versus the neural operators are more like a prediction model. So we're doing the image-to-image prediction, which means that, even if the initial condition change or boundary condition change or the physical parameter changes, you can still, throw that into the neural network, and then the neural network will spit out the corresponding prediction as an output, right? So that, opens up a lot more possibilities, right? In terms of where the neural operators can be used, right? In case of PIN, I think the biggest complaint in the classroom, right? We all agree that, in case of, physics-informed neural nets, we had to resolve the network whenever the condition changes. But that's not very useful from the engineering perspective. Versus here, once you train the model, then you can just keep reusing this for whatever problem that you're interested in solving. So as an engineer, like let's say you're working on some design problem, right? And you want to design, I don't know, the shape of an airfoil to produce certain aerodynamic quantities, properties. In case of a neural operator, you train your model on a bunch of simulations of the airfoil with different fluid velocity and blah blah blah. And once the training is done, then you can feel free to modify the cross-sectional geometry of the airfoil. You can change the fluid velocity and see how the response changes without having to retrain the neural network. So that's kind of nice thing about neural operators. Well, we have the MLP component in the architecture, except that the layers are now the continuous layers as opposed to the usual. So the overall structure is the same as MLP, except that instead of torch.linear and n.linear, we're now going to define our own custom layer that can handle continuous inputs and continuous outputs. Yeah. But the other part of the architecture is essentially the same. This may or may not be the advantage, but in case of the neural operator, the neural operators do not require a governing differential equation. So for some cases, that might be an advantage, right? Because not all problems, we already know the governing equation, right? There are actually many problems in engineering where we do not know the governing equation at all. And in case of PIN, if you don't know governing equation, then that's like useless, right? PIN is essentially just a simple regression model, input to output mapping model, and there's no use of PIN. In case of neural operator, we do not assume the existence of an available governing equation. So in case you have a problem where you don't know the governing equation of the system, you just have a bunch of data, neural operator might be a better deal, right? Although, if you do have a governing equation and somehow introduce that governing equation into the training of the neural operator, you can still do that. There's nothing prevents you from adding a physics-informed loss. If you look at the definition of the neural operator is just about the design of the architecture, and it's nothing about the loss function. So as long as you can, express, your governing equation, and then, somehow connect that with the neural operator, the neural network architecture, then you should be able to define a physics-informed loss, and then you can make it a physics-informed neural operator, or PINO, PINO, for that matter. And also, I mentioned that even though on the surface, it may sound like neural operators are simply just image-to-image translation problem, the actual meaningful contribution of the neural operator paper is that they define the problem in a continuous function space as opposed to the discrete pixel space. So we saw the things like Fourier neural operator and the graph neural operator. But there can be other formulations other than Fourier or graph. But nonetheless, the idea of neural operator generalized our previous understanding of the perceptron layers, the linear layers, into that integral operator, so that now instead of a discrete set of kernel values, we have a continuous kernel function, okay, learned by using Fourier, as a Fourier coefficient, or as some graph, message passing mechanism. And in that way, neural operators can be, resolution invariant, match invariant, and any arbitrary discretization. As a matter of fact, neural operators should be applicable. Okay. And then finally, there are lots of empirical experiments that shows that neural operators are actually more accurate than other deep learning methods. I was going to have a little bit of discussion, but for the interest of time, I'll just tell you the answer. So remember, the main difference is that the usual deep learning methods, we have the pixel-based formulation, whereas this kernel-based method, we have a continuous function-based representation. And in that continuous function formulation, we introduce things like Fourier transform. And Fourier transform with a small number of basis functions, you're automatically filtering high frequency noise, right? So naturally, Fourier layers, for example, are more robust to noise. Even if the input signal contains high frequency noise, by the virtue of having this Fourier decomposition inside of the layer, you're basically throwing away the high frequency noise components, and then therefore the algorithm becomes more robust. Whereas in case of the pixel-based formulation, each pixel can have any arbitrary value, right, as a result of the training. So there's a room for the model to go crazy, right, if you don't properly regularize your model. Versus in case of neural operator formulations, especially things like Fourier neural operators, it is more accurate. Same thing for the graph neural operators, as a matter of fact, because during the message passing, we have the signals from the local neighborhood kind of averaged out during the message passing. And then the averaging is an excellent way of eliminating noise. So even if the individual nodes vertices have some noise, by the virtue of computing the local average of those values, we can make the algorithm more robust. So that's kind of the interesting bonus that comes with the formulation of the neural operator. So with that, we're going to conclude the discussion about the neural operators. And then after the break, we're going to actually see the PyTorch implementation of Fourier transform, and then how we could use that to define a Fourier convolution layer. And then from there, we're going to actually construct our own Fourier neural operator and then apply it to solve a tiny little problem and then see how it works. So thank you so much, and see you after the break.